Okay, hello and welcome everybody to today's Saturday morning lecture, which is the second of 5 live stream events provided this spring. My name is Dr. Stanley Yen and I will moderate today's session. Because of COVID, our public lectures have moved online. Today, we welcome Dr. Ivan Prpic to teach us about the science of visual perception and how physics is used in optometry. The idea for today's lecture came about when I had my own eye exam last fall. I was impressed by how much physics is used in optometry today. This is definitely not my grandfather's eye exam. So I reached out to my optometrist and he went to the professional association and found Dr. Prpic to give us the lecture today. Dr. Prpic obtained his Doctor of Optometry degree from the New England College of Optometry in Boston. And because of his passion for optometry, he's been active in mentorship programs with students right across North America. Dr. Prpic currently practices at the Hollyburn Eye Clinic in North Vancouver, and he is in the process of building his own practice. So if you're looking for an optometrist, Dr. Prpic would be a good choice. In the live stream description, you'll find links to learn more about our speaker's career and accomplishments. Your questions for the speaker may be submitted via the chat box on the live stream. So without further ado, I would like to invite Dr. Prpic to give us the lecture on physics in optometry.
Thank you, Stan, for that great introduction. Let me just get my screen started here. All right, here we go. So thanks again, Stan, for that kind introduction, and thanks to all you audience members for taking your Saturday morning to come learn a little bit about eyes and physics and how it's used in optometry and during an eye exam. Hopefully we have some fun here and you guys all learned something. So as Stan had mentioned, my name's Ivan Prpic and I've been practicing here in Vancouver for the last 3 or 4 years after having worked in New York for the year prior to that. So to start off, I have no financial disclosure or professional disclosures. And let's start with some fun. We're going to start with some optical illusions and we'll see how the eye and the brain play tricks on each other. So let's take a look at this first optical illusion. And this illusion is something that we call the checker shadow illusion. And if I were to ask the majority of the audience members which of these two tiles, either tile A or tile B, was darker, most people would say tile A. But this is just an example of relative color perception and the eye playing tricks on your brain. And when we cut out the rest of the image, you can see that both tiles are in fact the same color. And the appearance of the lighter B tile is due to the shadow being cast by the green cylinder, even though they actually are the same color. And this here is something that we call the Titchener circles. And again, this is another example of your eyes playing tricks on your brain. If I were to ask the audience members again, which of these two orange circles appeared larger, most people would go on and say that the right circle appears larger. But when we cut out the background and the blue circles, we can see that both orange circles are in fact the exact same size. And this is due to something called relative size perception going on in the brain. And here's one of my favorites. This is something called the lilac chaser illusion, and this will be a bit more interactive. So if you look at this image, you can see that there's about a dozen pink circles forming one larger circle with a cross in the middle. What I would like you to all do right now is to lean into the screen and draw your attention to the cross right in the middle. And keep staring at that cross for about 10 seconds. What you'll all eventually notice is that the pink circles appear to disappear and a green circle appears to appear. And then when we switch our gaze again, we do see in fact that the pink circles are still there and there isn't actually a green circle that's there. And this is a combination of something called the Troxler effect and an after image being formed. And here's another very famous optical illusion. This is something called the cafe wall illusion. And when you look here, it appears that these blue horizontal lines are slanted and are not perfectly straight. But if we blur the image, you can actually see that every single one of those blue lines is running perfectly parallel to each other, and they are not actually slanted. And this is just a function of the eyes playing tricks on you one more time. This here is something we call the spinning wheel illusion. And what we have is 4 stationary circular images that when we move our eyes around the page, they appear to move in clockwise and counterclockwise rotations. But when we stop moving your eyes and focus on one of the images, we do see that they are not actually moving. Then this is another famous one called the scintillating grid illusion. And this illusion is comprised of a bunch of black squares with white circles between all the squares. And when you move your eyes around, there appear to be black circles that fill the gaps of the white circles. But when you try to find one of the black circles, it's not actually there and you can't actually find it. And this is caused by something called lateral inhibition. So we'll skip that. So let's get to some fun facts about the eyes. So the average person is supposed to blink somewhere between 15 and 20 times a minute. And this is how often we blink when we're doing our regular daily activities. Unfortunately, when we're staring at screens, computers, cell phones, tablets, our blink rate drops from about 20 times a minute to about 5 times a minute. This is why people have severe issues of dry eyes the more computer screen hours they use per day. Omatophobia is the fear of eyes, so I'm assuming most people here do not have that fear if you're watching this presentation. A fun fact about animals, so an ostrich's eye is bigger than its brain. This is something to do with the brain's function. So 50% of the brain's function is dedicated to visual processing. That just puts into perspective how much information we actually gather through our visual processing system. And this is one for all you photographers out there. If the eye was a camera, it would have approximately 576 megapixels. And to put that in perspective, the new iPhones only have about 12. So the resolution of our vision is pretty darn good. So what is an optometrist? An optometrist is a primary eye care doctor who specializes in ocular disease diagnosis, management, and treatment. A big part of our profession involves visual optimization. This is through the use of glasses, contact lenses, and sometimes we recommend laser surgery for the patients as well. And this is all done with the use of physics in the human visual system. So here's a little video I put together of an actual eyeball. So when we're looking at the health of the eye, what we do is come right on in through the pupil. And there are a few structures we pay very close attention to when we're making sure the eyes are nice and healthy. The first is that disc that I'm circling with the mouse right there. And that disc is a part of the eye that we call the optic nerve. And the optic nerve is a cable that essentially connects the eye to the brain. So I always describe the eye as being a satellite dish that collects light, it turns it into electricity, and then sends it back to the brain through this cable. It's obviously not that simple, but the analogy works. The next part of the eye that we look at is the dark spot that's found right adjacent to that optic nerve. And that dark spot is a part of the eye that we call the macula. And the macula is a part with the best vision. So when you're looking somewhere, all the light in the eye, in order to be seen clearly, needs to be focused right on that dark spot. The third thing we look at are the blood vessels in the retina. That's what we see in the peripheral parts of this image. And we look at that portion of the eye in people with systemic diseases such as diabetes, high blood pressure, any type of autoimmune conditions. And there's a lot of systemic diseases that do in fact manifest in the eyes. So here's a slightly more detailed schematic of the eye with a few more structures being labeled. And this is a cross section that we essentially cut straight through the middle. And starting on the front, there's a part of the eye that you're all familiar with called the cornea. And the cornea is the clear surface on the most anterior portion of the eyeball. And the cornea, that's the part of the eye that's responsible for refracting the majority of light. The cornea has a lot of pain receptors. So this is the part of the eye that's extremely sensitive when you get an eyelash stuck in your eye if you scratch the eye. The next part of the eye when you move back is the part called the iris. And the iris is the aperture of the eye that controls a muscle that gets larger and smaller depending on how much light we want to let through this aperture. And this is the part that some people have blue irises or brown irises or hazel irises. The pupil is found in the center of the iris, and this is the actual aperture where light travels through. If you're in a dark room, this pupil will get nice and large so that more light can enter. But if you're in a bright room or in a bright sunny day, the pupil will get smaller to limit the amount of light going in. The lens, that's the structure that's just behind the iris and the pupil. And this is the portion of the eye that's responsible for focusing light onto the macula. Then as we move back towards the back of the eye, you can see the macula that we spoke about earlier. And the macula is the part with the best vision. And the macula has the highest density of a photoreceptor that we call cones, that you've all maybe heard of. Then the vitreous, the inside of the eye isn't actually hollow. It's filled with this gel known as the vitreous. And what the vitreous does is it helps the eye keep its shape, and it helps with protection whenever the eye gets any type of trauma. So some common eye diseases you guys have maybe heard of, those being cataracts, macular degeneration, glaucoma, diabetic retinopathy, and these are fairly common diseases. And what are they exactly? So what a cataract is, it's a clouding or discoloration of the lens of the eye. And if you look at this image of this individual, you can see that his right eye on the left side of the screen is nice and dark, and you can see his brown eye. On his left eye, on the right side of the screen, you can see that there's a cloudiness that's right behind the iris. So cataracts are a regular age-related change in the eye, and we all get cataracts at one point in our lives. This one, unfortunately, however, is asymmetric, and this individual looks much younger, so this could have been caused by a bunch of other conditions or trauma, perhaps. And the treatment for cataracts is we refer to a cataract surgeon who actually surgically removes this lens and puts an implant in its place. Macular degeneration. What macular degeneration is? It's damage to the retina, causing loss of the central vision. So we were describing these photoreceptors earlier, and the macula has a very high density of these photoreceptors called cones, and these cones are very metabolically active. And when these cones are metabolically active, they produce a lot of waste. And when this waste starts to accumulate, if the eye cannot flush out the debris as fast as being produced, you start to see these white deposits that accumulate around the macula. So you have a surface that's supposed to be nice and smooth and flat that now becomes bumpy due to the accumulation of this waste. Glaucoma. Glaucoma is another condition that a lot of people have heard of, and it's most commonly an age-related condition that's damage to the optic nerve that's typically due to an elevated eye pressure. So if you focus on the photo on the left of the screen, you can see the image of the optic nerve. There's a pinker part on the outside with a whiter part in the middle with some black arrows overlaying it. And I always like to describe the optic nerve as a donut. So the pink part's the donut and the white part's the donut hole. And what we see in glaucoma is an increase in the size of that actual donut hole. And this is a sign of loss of the tissue that's adjacent to it. This here is an image with someone with fairly severe changes to the retina due to diabetes. And diabetes, unfortunately, is the most common, it's the leading cause of blindness in the middle-aged population in North America. So diabetes not only affects the rest of your body, but can significantly affect the blood vessels in your eye. And when that occurs, you start getting leakage of either blood or proteins out of these vessels. So how does physics correlate to optometry? First and foremost, the art of optics. The art of prescribing glasses and contact lenses is fully dependent on the laws of physics and optics. And we need to know exactly what power of lens to put either in your glasses or your contacts so that you can see clearly. Photometry. And what photometry is, it's the science of measurement of perceived light. Color vision, the correlation of rods and cones to wavelengths of color. And then gross electric potential. So what a gross electric potential is, it's a summed electrical activity of neurons. And in order for us to see, there's actually a charge that gets created from the front of the eye relative to the back, and then from the eye relative to the brain. So here are some terms you've all maybe heard of. What does 20/20 actually mean? What does it mean to be nearsighted, which is also known as myopia? What does it mean to be farsighted, which is also known as hyperopia? Then what is that dreaded astigmatism? So let's start with that 20/20. So what that 20/20 is, it's something that we call the Snellen fraction. And the numerator, the upper 20, that's corresponding to the letter distance. Then the denominator, the lower number, that's corresponding to the letter size. And the reason we use the 20 is because it's customary to test this vision at 20 feet. So that numerator actually corresponds to 20 feet distance for a testing distance. And the reason I have the 6 on the right side is because there are some places in the world that actually use meters instead of feet. So their equivalent vision is 6'6", which is 6 meters over the letter size 6. And this here is something we call the Snellen chart. And this is something a lot of you have maybe seen at your doctor's office, at your optometrist's office. And this chart is named after a Dutch eye doctor named Dr. Herman Snellen. And this chart contains a range of letter sizes all the way from 2200 way at the top to 2010 way at the bottom. So a 2200 letter is about 10 times as big as a 2020 letter. And a 2010 letter is half the size of a 2020 letter. That's simply due to these ratios that exist in the Snellen fraction. So how big is this 2020 letter? And the exact definition of the 2020 letter, it's the size of a letter on the 2020 line that subtends 5 minutes of arc at a distance of 20 feet. So let's break down what a minute of arc actually is. Before we get to that, let's talk about the differences in letter sizes. So a 2040 letter, as I described, is twice as large as a 2020 letter. So if you were told that you have 2040 vision, you can see at 20 feet what the average person can see at 40 feet. And let's break down what a minute of arc actually is. So a minute of arc is an angular measurement equal to 1/60th of a degree. So one full rotation of a circle equals, one full rotation of a circle equals 360 degrees. And therefore that equals 21,600 minutes of arc. So the schematic I have down below, this shows a big letter E. And if you're standing at the apex of that triangle, right at 20 feet, this E, the 2020 letter, will subtend 5 minutes of arc in your pupil. So why do we always use this letter E, and how do we break down this actual optotype? So the thickness of a brushstroke of the optotype at 20 feet is 1 minute of arc for the 2020 letter. So therefore, in order for your eye to see 2020, your eye needs to be able to discern 1 minute of arc in regards to spatial vision. So the size of each of these pieces, the components of the E, is 1 minute of arc, and if you add all 5 of those components, that's the 5 minutes of arc we talk about. And the actual linear size, if you measure this 2020 letter, is approximately 8.87 millimeters. So how do lenses correct prescriptions? So light converges and diverges, and we use convex and concave lenses to correct this. Lenses can also act as prisms, and what a prism is, it's a transparent object that refracts light, and some prisms can separate white light into its constituent colors. What an aberration is, it's a failure of a ray to converge light to a single point. So there are 2 types of aberrations. There's high order aberrations and low order aberrations. Low order aberrations correspond to things like nearsightedness or farsightedness that we had talked about. Then high order aberrations are due to imperfections in lens materials, and they're due to things such as prisms bending light of different wavelengths to different degrees. What an index of refraction is, this is a measurement of how fast light travels through a material. So glass will have a different index of refraction relative to different types of plastic. And what is the actual number in your prescription? Let's get to all of this. So the use of lenses. So here we have 2 basic thin lenses, and a lens is a piece of material used to refract light and create an image. On the left, we have a convex lens or a converging lens. Then on the right, we have a concave or a diverging lens. So a convex lens takes light that is traveling parallel and converges it to a focal point. And with the convex lens, a real image is formed at the focal point of the lens. For a concave lens takes light traveling parallel and diverges it. Sorry, there's a bit of a typo there, but it diverges the light. And the focal point of a concave lens is posterior to the lens itself, and is a virtual image being formed. So how do we determine the actual power of a lens? And the unit we use to describe the power of a lens is a diopter. And what a diopter is, it's a unit of measurement of a power of a lens or a mirror that is equal to the reciprocal of the focal length in meters. So if we have either a concave or a convex lens with a focal point of 40 centimeters, how we determine the power is we find the reciprocal of that distance. So for a 40 centimeter focal point, it's 1 over 0.4 meters, which is 2.5 diopters of power. So the human eye is a lens. So the main refracting elements of the eye are the cornea and the lens. This is a very simplified model, but we'll use this for explanation purpose. And in order for an eye to perceive a clear image, the image being formed by the eye must be formed on the retina or the macula in specific. So what is the dioptric power of the human eye? So the average human eye in the simplified model is about 60 diopters. And the cornea is responsible for 40 of those diopters, and the lens is responsible for about 20 of those diopters. So if we take the full power of the eye, its focal point is about 16.7 millimeters posterior to the surface of the eye. So the human eye is a lens again. So these red beams are meant to act as light beams traveling parallel into the eye. Then in order for an image to be seen clear, the light must converge right on the center of the retina or on the macula. So what does it mean to be nearsighted or farsighted? So someone who is nearsighted, the focal point of their eye is anterior to the retina, meaning the eye is either too long or the power of the eye is too strong. For a farsighted individual, the opposite is true. For people who are farsighted or eyes that are farsighted, the focal point of the eye is actually posterior to the retina itself. So the eye is subsequently either too short or the power is too weak. And let's kind of break this down even further. So this is what the ray diagram of someone who's nearsighted would look like without correction. For light that's traveling parallel, it's converging to a point that is anterior or in front of the retina. So this person is going to see a moderate amount of blur due to the focal point, the image not being created on the retina. So how do we correct this? We use a diverging lens. So before I get to that, so for farsighted individual, that's the opposite. The light is focused posterior to the retina, and they will again also have some degree of blur. So how do we fix this? The use of lenses. For a nearsighted individual, what we do is we use a diverging or a concave lens. So what the concave lens does is it moves the actual focal point of the light posterior so that it is in line with the retina. And for a farsighted individual or someone whose eye is too weak, we use a convex lens to converge the light so that it moves the focal point from the red vertical line here anterior or forwards towards the front of the eye so that it's in line with the retina. And for this, and in order for the eye to see clearly, this is what needs to occur. So to summarize the difference again between a nearsighted and a farsighted individual. So people who are nearsighted, as a generalization, they can see well up close, but have poor distance vision. And this is due to the fact that the eye is either too long or the dioptric power is too strong. So the focal point is in front of the retina. And this is again corrected with the concave lens. And then for farsighted individuals, as a generalization, we say that their distance vision is better than their reading vision. And in these people's eyes, their eye is too short or the dioptric power of the eye is too weak, which leads to the focal point being formed behind the retina. And then this is corrected with a convex lens. So what is astigmatism? This is that dreaded word I'm sure most of you have heard about. And spoiler alert, the good news is astigmatism isn't any bad disease with the eye. And what it is, it's a mismatch of the curvature or the shape of the eye. And this astigmatism can cause issues with overall acuity, especially during tasks such as night driving, when it's raining, when you're tired, these types of things. And people often get told that an eye with astigmatism is football-shaped or egg-shaped eye. That's a slightly simplified approach, but it allows us to visualize it. And what's actually going on is there are two meridians in the eye, let's say a vertical meridian and a horizontal meridian. And if these meridians don't have the same dioptric power, they're going to have two different focal points. And then if the eye has two different focal points, that's what astigmatism is. And to take it the next step further, this astigmatism isn't always oriented vertically and horizontally. It can have an orientation at any particular degree, ranging from 0 to 180 degrees. So this is a bit of a schematic that I put together showing what an eye with astigmatism is like. So if light is traveling parallel, the red rays of light are being focused posterior to the retina, and the blue beams of light are being focused anterior or in front of the retina. So this is subsequently leading to two different types of blur found within the eye. So let's talk about the numbers on your glasses prescription. So some examples of a nearsighted prescription that you guys may have seen are minus 2.00 SPH. And what that SPH stands for is sphere, or minus 1.75 sphere. For someone who's farsighted, they'll have a positive number, plus 1.50 or plus 2.25. And these numbers correspond to the type of lens being used, whether it's a concave or convex, and they correspond to the dioptric power we need to put inside the lens so that you can see clearly. And when we look at the examples of someone with astigmatism, there's a few more numbers here. The first numbers, the 150 or the 350, correspond to the farsighted or the nearsighted powers. Then the second and third sets of numbers, the minus 0.75 x 180 or minus 2.25 x 90, those correspond to the power of the astigmatism and the axis that it's oriented at. So how do we actually determine the prescription? So we determine the prescriptions through the use of this fancy gizmo that we call the phoropter. And the phoropter is really a magnificent piece of engineering that contains a lot of lenses inside, and it really allows us to accurately and precisely measure your true prescription. The main purpose is to figure out your actual glasses prescription. They do a handful of other things, but we won't get into that in too much detail. And this is the test we always talk about. What is better, option 1 or option 2? But this isn't all that your glasses do. And if there's any rock fans here, you might recognize this image. And this image is the actual album cover for an old Pink Floyd Dark Side of the Moon album. And what this album cover has is a prism that's taking white light and bending it into its constituent colors. And so what is a basic prism? So a basic prism enters light, and it always bends towards the base. And when the light ray bends towards the base, the image appears to move towards the apex of the prism. So if you're an observer on the right side, at where this eyeball is, if you're looking at a ray of light through a prism, it's going to appear much higher than it actually is in the real world. And we use this for a handful of conditions for the eye as well. So we use it for something that we call a crossed eye or a lazy eye. So this particular set of eyes, you can see that the person's left eye on the right side of the image is actually slightly turned inwards. And this is something that can actually cause issues if it's not treated or managed early enough in life. So how we fix this is by using a prism, or we can surgically do it, to redirect where the light is focused on the eye. So if you look at the schematic on the right, in order for the eye to be seen clearly, that red ray of light needs to be focused directly on the X. So how we do that is by incorporating a prism. So what this prism does is it bends the light so that it's focused right in front, in line with the macula, to correct this lazy or crossed eye. So wavelengths and color, this is something that obviously comes into significant consideration when we're talking about vision. And you guys have all probably seen the electromagnetic spectrum. And everything that we see in the world, everything that our brain and our eyes perceive, is found within this visible light spectrum. And it's ranging from 380 to 7080 nanometers. So we've all heard about ultraviolet light and infrared light. So these are actual types of light that we don't see, but can actually cause harm to the eyes if we don't protect them. The good news is the majority of the harmful ultraviolet and infrared light actually gets absorbed by various components of the eye. Over 98% of light under 380 nanometers gets absorbed by the cornea and the lens. And only 1 to 2% of UV light from 300 to 360 nanometers makes it to the retina. And there's a lot of research that looks to this, and you guys have probably heard about these blue light blocking glasses. And the basis of that is that people suggest that there's a portion of the visible spectrum ranging from 380 to 450 nanometers that still enters the eye, but can in fact be harmful or damaging to your eyes. So colorblindness. So colorblindness occurs when individuals are missing a part of their photoreceptors that we call the photopigment. And you guys have maybe heard about rods and cones, and we'll get a bit more into detail of that later, but there's two main types of colorblindness. There's red-green colorblindness and blue-yellow colorblindness. Then red-green colorblindness is broken up into two types, deuteranopia and protanopia. And this is actually a relatively common disorder, and in some populations, as high as 8% of males and 0.5% of females have an issue with their color vision. The blue-yellow colorblindness, known as tritanopia, unfortunately isn't quite as common, and it's a lot more rare. So having color blindness doesn't necessarily mean the eyes are unhealthy. It just means you're having some dysfunctional photoreceptors. And the reason we care so much is because when we're learning in school, sometimes kids don't realize that they're colorblind, and we want to make sure that their teachers are aware that if they're instructing to, let's say, look at a red square or a green circle, some kids can't discern the difference and teachers won't realize it. So we want to make sure that they're aware of this. And the other reason is some jobs require pristine color vision. I would hate for someone to be passionate about becoming a pilot, going through all the instructions, only to find out that they're colorblind and unable to pursue that career. So here's a cool example of what people see when they are colorblind. The upper left image represents 3 nice parrots with vivid colors, and this is what someone with quote-unquote normal vision sees. The image on the top right is someone who's got a deuteranomaly or deuteranope, and this is someone who's got that red-green issue. The image on the bottom left, that's what someone who's got protanopia sees. So it's very similar to the deuteranope with some missing reds. Then what the tritanopia is, you can see quite a bit more blues and reds in the image, and they're the ones who have a tough time discerning the blues and the yellows. I'm not sure if there's anyone in the audience who has some color vision deficiencies, but something to be aware of is a lot of technology these days, whether it's iPhones, your computers, there's actual settings that you can change to make the cell phone more accessible so that it's a bit more catered to your particular vision. And you guys have maybe heard of some color vision glasses. One famous one is called Chroma. So these glasses, if you were to do a color vision test, they wouldn't actually improve your ability to discern colors, but what they do is they change your perception of the colors. So it's something worth trying if you wanted to see what kind of effect it has on your eyes, but no guarantees. So rods and cones. So rods and cones are the 2 types of photoreceptors that exist inside the eye, and they form something called the duplex retina. And the duplex retina consists of 2 main types of vision. There's something called photopic vision, and there's something called scotopic vision. And photopic vision occurs under bright lighting. So this is when you're in a bright room, you're out on a sunny day, and this is when the cones kick in order for us to see clearly. Scotopic vision, on the other hand, occurs under dim lighting. And this is when you're in a dark room, when you're outside at night with no sunlight or no lights. And then what mesopic vision, it's a combination of the 2 other scotopic and photopic visions. And what this is when both types of vision are activated, and this is typically found under twilight conditions. So let's say dusk or dawn, or when you're in a very dimly lit room. Then the 2 classes of photoreceptors we talk about are the rods and the cones. So to kind of give a bit more detail on these particular types of vision in the duplex retina, let's talk about the photopic vision. And the photopic vision kicks in under bright conditions. It's mediated by cones, and the photopic vision has very good visual acuity. So this is the part of the eye that allows us to see 20/20. Another big feature of the photopic vision is that it has very good color discrimination. The downside of the photopic vision is that it has very poor sensitivity to low light and changes in light. Scotopic, on the other hand, as we had mentioned, is active under dim conditions. It's mediated by rods. It has very poor visual acuity. So if you're measuring your scotopic vision, it's only able to see about 2200, believe it or not, which is 10 times worse than the photopic visual system. The scotopic vision has very poor color discrimination, so things look mostly gray. But the feature of it is that it's very, very sensitive to low levels of light, which is why it kicks in when it's dark out. And let's briefly talk about gross electric potential, since I had mentioned this at the beginning. So a gross electric potential is a summed electrical activity of a collection of neurons, all right? So when this occurs in a few ways in order for the eyes and the brain to perceive vision. The first is the front of the eye has a positive charge relative to the back. So when light enters the eye, it hits the cornea, and the charge at that portion is different than at the retina, which is the back part. And we can measure this using something called an electro-oculogram, or an EOG. And this is very beneficial for some particular types of eye diseases. The second charge that exists is something called, is a retinal electrical potential that is elicited by a flash of light. So if we measure the electrical response of the retina itself, when light enters, we find and we can quantify a charge. And we can measure this with something called an electroretinogram or an ERG. And this, again, is something that can be used to diagnose some particular diseases. The third is the brain has an electrical response to a potential that is sent from the eye posterior to the brain. And we call this a visual evoked potential. And this, again, is used for lots of issues, lots of diseases that correspond to the nerve tissue. For example, multiple sclerosis is something that we sometimes need to do these tests on. But again, the point being, there's electrical signals being sent back to the brain whenever we use our eyes to see. All right, so that's all I've got for the presentation today. Hopefully, I didn't keep you guys too long, and hopefully it was interesting and you guys all learned something. So Stan's going to take over, and I think he'll help pass on any questions any of you may have, and I'll happily answer them. And if you guys have any questions, feel free to reach out to me at any point. I'll gladly give you guys some more input on how physics is correlated with the eyes. If any of you guys are interested in optometry, absolutely reach out to me and I can talk to you about that as well.
Okay, so I invite anybody with questions to post them on the chat box on the YouTube channel. So I'll just start off with one question. If a high school student were interested in optometry as a career, what courses should they take in high school, and how do they go about getting into optometry school from university? Do they need to get a bachelor's degree first, or how does that go?
Yeah, so that's a great question, Stan. So most optometry schools do require a bachelor's degree. There are a few that do not actually require the bachelor degree, and you can transfer in after 3 years and complete your bachelor once you get to the particular optometry school. So the majority of classes you'd want to take are kind of the general sciences or the pre-med route. There's a lot of individuals in my class who kind of went that pre-med route or went that Bachelor of Science. There are a lot of people who actually do other undergrad degrees, which is absolutely okay. There may just be a few other prerequisites that you're required to take. The big ones are physics, chemistry, biology, organic chemistry. These are the big topics. They require you to usually take some psychology classes and some English classes. So most of the classes are the same prereqs that you would have for other health professions such as dentistry, physiotherapy, or medicine.
Okay, another question is, how did you make that eye video? How did you capture that image?
Yeah, so there's actually an amazing retinal imaging device that we use at our clinic here in North Vancouver. And it's an imaging device that captures a very wide field of the retina. Traditional cameras, they only capture a very small area. Let me go back a bit to show you. So traditional retinal cameras, they only captured an image that was about this size, right? So it kind of showed you the important structures, showed you the optic nerve, and it showed you the macula, and it showed you some of the blood vessels. But there's a very large portion of the retina that unfortunately doesn't get captured with this image. And this retinal imaging device is called an Optos, just is a very wide field image. And the software that we use actually is able to create one of these three-dimensional images and a small video that's nicer for presentations. And a fun fact about this image that I showed you the video of, this is actually an image of my eye. So hopefully that answers your question a little bit, Stan.
Okay. Another question is, are there any corrections beyond glasses for color blindness?
Yeah, so color blindness, that's unfortunately not something that we've able to figure out a way to truly correct. So there's two types of color blindness. It can either be acquired or genetic. And if you have a genetic color deficiency, it's due to the eye missing some of its particular photoreceptors or photopigment that is found in these cones. So there isn't actually a way that we can repair or replace these cones that are faulty or missing inside these people's eyes. There are a lot of tints and filters that we can use in our glasses, whether it's an amber tint or a yellow tint, or there are some kind of light red tints that we use. And these don't actually improve someone's color vision. They just attempt to increase someone's ability to discern different colors and their ability to kind of perceive the colors that are actually there. But there isn't actually any technology or surgeries or medications that can truly grow these photoreceptors that we're missing. To kind of go off on that question, people often ask about different modalities to correct your actual glasses prescription. And the three main types that we typically talk about are glasses, contact lenses, and laser eye surgery. Glasses, they're the simplest option. You have a frame and you put the lenses in front of the eye, and we can put any magnitude of any particular power on the lens and it doesn't rotate. We can put just about any magnitude of prescription contact lenses as well, but once we start doing that, it starts becoming a bit more finicky. Because in order for someone, especially someone with astigmatism, to see clearly, the contact lens needs to be oriented a particular way. So when we put a contact lens in the eye, we need to know exactly how it's rotating and how it's spinning in order to orient the prescription properly. In contact lenses that correct for astigmatism, they're actually weighted on the bottom so that they know where to sit properly in order to give a clear image on the retina. There are a handful of types of contact lenses. The majority of contact lenses that people typically use are the soft contact lenses, but there are a few types of hard contact lenses as well. Hard contact lenses, we typically call them rigid gas permeable lenses, are able to correct some particular conditions better than soft contact lenses. A third type of contact lens is a scleral contact lens, and this is a lens that actually vaults over the entire cornea and doesn't actually sit on the cornea. And the benefit of these is that they can provide optimal vision for people who even have diseases of the cornea in ways that glasses or soft contact lenses cannot. Some of you have maybe heard of something that we call orthokeratology as well. Orthokeratology is a type of contact lens that you actually wear when you're sleeping. So you put the contact lens in before you go to bed, you sleep with it for the full 8 hours, and then you wake up and you take the contact lens out. And what this contact lens does, it essentially reshapes the front of the cornea so that you can function throughout the day without the need of contact lenses during the day or glasses. So that's a fairly amazing piece of technology that a lot of people don't even know exists. And then the next way we correct your prescription is due to these laser eye surgeries. And there's a few types of laser eye surgeries. The most common type that people are familiar with is something called LASIK. There's a few other types called PRK, one called SMILE, and there's also some implantable lenses that we do for people with high prescriptions. LASIK, so PRK wasn't around initially, kind of in the early 90s, and LASIK soon thereafter took over the market. The reason LASIK took over the market was because it had a slightly faster healing time, and people had slightly more instant gratification in the vision. And the big difference between LASIK and PRK is that LASIK creates a flap on the cornea. You lift that flap up, you reshape the cornea, and the flap gets put back down. For PRK, there's no flap that's formed at all. So you just kind of reshape the tissue altogether. So it takes a slightly longer time to heal. PRK has started becoming a bit more popular again in some surgical centers because the long-term safety profile is a bit better and the long-term vision is slightly more ideal with less aberrations within the eye. So I know I digressed a bit from your initial question, but hopefully that clarified some questions some people may have had, Stan.
Okay. Another question is, what are the professional recommendations for limiting long-term damage caused by digital screen exposure? Is there a real hazard there? Should we set our screen so that we cut off the blue part?
Yeah, so this is the hot conversation for anyone in eye care right now, and the literature is kind of mixed. So the first thing researchers and vision scientists looked at was how the blue light that's emitted from screens affects your sleep cycle. And what we do know is that the more exposure you have to blue light, the more fluctuations in your melatonin levels you'll have. And what melatonin is, it's a hormone that regulates your sleep. So what the literature has shown is that people who stare at screens, whether it's during the day or at night, they'll have less high quality REM sleep and their sleep cycle will be slightly more irregular. The second thing that the vision scientists are looking at is how the blue light affects the eyes on a cellular level. And what we do know is that light is damaging. So in theory, light with more energy is more damaging. So light with shorter wavelengths, that's the blue light, the ultraviolet light, in theory has more energy than red light, and it can subsequently cause more damage to the tissue. So we do know that this exists on a cellular level, but the question is there enough energy in blue light actually emitted from screens and devices to make a difference? This is where the literature isn't very sure just yet. So the science makes sense, but we're unsure if the magnitude of blue light coming from screens will actually be enough to cause issues. Because if you measure that magnitude, relative to sunlight that we're exposed to every day is extremely disproportional in that you're getting far more blue light from the sun. The third thing that the vision scientists are looking at is how the blue light affects the eyes on an eye strain, headache, tired eye standpoint. This is where there hasn't really been any good placebo-controlled, double-blinded studies that I know about. It's mostly anecdotal. And the basis for these claims is that blue light has a shorter wavelength, therefore it's going to bend more as it's entering the eye. And if the light is going to bend more as it's entering the eye, it's going to cause more scatter of this light. And if it's scattering more when it's within the eye, it's going to cause more disruption in your photoreceptors. And that's what people postulate is leading to a lot of these symptoms of digital eye strain and computer vision syndrome and just overall discomfort when we're staring at screens a lot. So the question is, well, should we be doing these blue light blocking glasses? So there is a very high potential benefit, but it's hard to know if it's actually protecting the eyes to the degree that a lot of these claims are actually making.
Okay, is ultraviolet light definitely known to be a risk factor for macular degeneration?
Yeah, so we do know that ultraviolet light is absolutely damaging. But the good thing about ultraviolet light, as we had mentioned in that slide, is most of it doesn't actually enter the eye. So if the anterior structures of the eye, so let me just pull up that diagram. So this right here, if you look at this model, in order for the light to damage the retina, it has to pass all the way through the front from the anterior portion. It's got to go through the cornea, through the pupil, through the lens, through the vitreous, and then it's got to hit the macula. So the good news is the majority of ultraviolet light actually does get absorbed by the cornea and the lens. So if we did not have a cornea protecting the eye and the retina, if we did not have a lens protecting the eye and the retina, the ultraviolet absolutely would cause issues and damage to the retina.
Okay. What are some of the practices that you would recommend to promote good eye health?
Yeah, so that's a good question that we talk about every day here. And I always say, as a rule of thumb, healthy body, healthy eyes. The first is the eye is very cardiovascular. There's a lot of blood vessels going in and out of the retina and the rest of the eye. So stay fit and stay active. The more blood flowing in and out of the eyes, the better. So if you can be active and if you can reduce the risk of developing some of these systemic conditions, such as high blood pressure, such as obesity, such as diabetes, your eye is going to absolutely reap the benefits. The second is diet. Everyone knows this. Eat healthy. I'm a big believer that what you put in your body really does make a difference on your overall health. So if you eat those leafy greens, stay away from the processed foods, simple sugars as much as you can. I'm a big believer in omega-3s. These are all things that will actively promote good eye health. There's a few particular eye vitamins that you guys have maybe heard of, and those are lutein and zeaxanthin. And these are pigment molecules that are found in very high concentrations in the macula. And there are a handful of eye diseases that have been shown to decrease the concentration of these pigment molecules. So there are some people we actually recommend vitamin supplements to decrease the likelihood of some of these eye diseases progressing. The third thing that I always recommend people is sunglasses. We've spent a while talking about the damaging effects of light. So the same reason you want to wear sunscreen, you want to wear sunglasses to protect the eyes. There's a very high correlation between people who live in very sunny areas near the equator and their incidence of some diseases such as early cataracts or macular degeneration. So I love the sun. I'm out in the sun always, as often as I can be. But it's always a good habit to get into, to wear those sunglasses to not only protect the eye itself, but also to protect the tissue around the eye so you don't develop any skin issues there as well. So those are 3 habits I routinely talk to people about. Another thing about the active lifestyle is, so nearsightedness, also known as myopia, is becoming more and more and more prevalent across the world. And in some areas in the planet, there's about 85% of school children who are nearsighted. So as you become more and more nearsighted, there are some risks associated with this, with higher magnitudes of nearsightedness. So there are a few steps we can do, or a few techniques we can actually incorporate to reduce or minimize the likelihood that your prescription is going to change drastically year after year after year. The number one factor that we can control in order to reduce the risk of our nearsightedness progressing is time outdoors. So there's been study after study showing that if you spend more than 90 to 120 minutes outside, your likelihood of developing nearsightedness will significantly drop off. There also is a correlation to near work, such as screen use, and the likelihood of your nearsightedness progressing. So I always tell people just use those screens in moderation. Unfortunately, over the last year of our lives, that has been very hard to do. We've gone from living in the real world to staring at our screens all day. A lot of you students spend all day on your laptops and your tablets at school, then you get home and you have to study. So I know that there's no way around that, but I always just remind people something called the 20-20-20 rule. So whenever you're doing near work, every 20 minutes, try to take a 20-second break, blink 20 times, and look 20 feet away. And this is something that just gives you a bit of a reminder to take the breaks during these prolonged activities of near work. Hopefully that gave you a long-winded answer, Stan.
Okay, those are all excellent points that we should all take to heart. So I think our time is almost up. So with this, I would like to thank Dr. Prpic for this very interesting lecture this morning. And so I hope to see you all again at next month's lecture, which will be on March the 6th. So thank you all again.
Thank you, Triumph, and thank you all you audience members for spending your Saturday morning